The states on the right and the states on the left, two different neighbors. No.
Same hydrogen, whether it's up or down.
Stickers.
So it's a through bond coupling going through the, not just the spin states of the proton nuclei and the carbon nuclei, but the electrons in between them. We've kind of skipped over that.
So the electrons are just doing the same thing.
Yeah.
In this.
Yeah. And the only change between here and here is the carbon. Only change between here and here is the carbon. The difference between these two is the proton. And maybe the electron so that they pair up with the proton.
Yeah.
Sheldon?
So again, I might have missed something. The higher ground state, why is that one a higher energy than the lower ground state? Like you were saying, is that a higher resistance?
Because these are all paired. So if you go across here, the carbon nuclei is up, the electron next to it is down, this electron is up, this one is down. So now we have all spin states paired like they want to be. This one has the two spin states going up, which is unfavorable, right? And so it actually wants to flip a little bit more because then it at least pairs the spin states. But then it's against the magnetic field, so it's kind of it's still, this is the higher energy of these two.
So the one on the bottom is with the
Yeah,
magnetic field,
yeah,
right?
yeah,
And when it's against is when it has a higher energy state.
yes. Okay, now that we drew it all out, is it a little more clear? Not entirely.
Not really at all.
What do you want me to do with that? Re-explain it.
Yeah.
Okay, let's go through it one more time. Okay? We'll start with the carbon.
I think application would be right now.
All by itself has this energy difference between the two spin states. The carbon is not by itself though. It has neighbors. And so it's bonded to a hydrogen with the two electrons. In this one, the carbon is aligned with the magnetic field and all the spin states are paired. And so that's actually the lowest ground state. When we excite it, it's now against the magnetic field and we're not pairing the spin states between the electron and the carbon. So it's much higher in energy. It's a greater energy difference to get from the ground state to the higher state. The alternative is to have the carbon with the magnetic field, but it's not paired with its neighboring electron because the proton is with the magnetic field as well. So you can't get both of them with the magnetic field and paired at the same time. This is the one bond coupling. It's different than the ones we've been talking about. When that carbon does a spin flip, then it's all paired, but carbon's against the magnetic field, so it's not as, or it's in the excited state. So this one is lower than this one because they're all paired, but these two are going to be lower than either of those because carbon's with the magnetic field. A little better? Sorry. Anita?
Can you say which one is with the magnetic field?
So we're talking about this being our magnetic field. Up is aligned with the magnetic field, down is not.
So what exactly is causing the tiny little fragmentations? Which one of those cases is causing the splitting coupling issues?
Well, now we have two,
Okay.
right? We've taken one signal and put it into two signals. And
Oh, okay.
one of these is here and one of them is here.
Gotcha.
And remember that proton's going to be in the plus and minus state about 50% of the time.
So what happens when it's decoupled? Is there
Then the proton just excited that it sees the average and it goes back to the original.
And it goes back to the.
Okay, a little bit closer. Okay.
I think so.
This is not a coupling we see as often because we don't do the proton decoupled, and so it's only when we have a direct attachment between a carbon and a hydrogen, and we may see it in the proton NMR. And the main thing I want you to take away from it is that the JCH is going to be approximately correlated with the hybridization of the carbon that's in the bond. So if we have J, or one bond J between the C and the H, it's going to be approximately 500 hertz times 1 over n plus 1, where n is the hybridization state of the carbon. So if n is 1, you're going to have 1/2 times 500, about 250. If n is 2, so we have an sp2 hybridized carbon, it's going to be 1/3 times 500, so it's a slightly smaller coupling. So your CH is going to be higher, or larger number for your CH coupling than for your CH2 than for your CH3. No, sorry. Let's just tell me you're attached. CSP greater than CSP2 greater than CSP3. So you'll have an approximate correlation, maybe around 250 for the SP. 1/3 of 500 would be more like 175-ish for the SP2, and then 1 divided by 4, so 1/4 of that, 125 for your SP3. These are all approximations, they'll be within a range, but generally your coupling for your SP is going to be greater than SP2, greater than your SP3. Ready to move on? Okay. Now we're going to look at the 2-bond coupling. Now we're going to go back to hydrogen-hydrogen, and the rest of these are going to be hydrogen-hydrogen, where you have a geminal coupling. Geminal refers to 2 atoms that are attached to the same carbon. So I'm going to use 2-bond and J2 and geminal all interchangeably because they all mean the same thing.
Could you use the definition for geminal?
Geminal is 2 atoms, in this case 2 hydrogens, they're attached to the same carbon. And generally we talk about the hydrogens. In this case we have a small J value. It's usually smaller than J1. So your 1-bond coupling usually it's going to be usually negative. For hydrogen. But do we see that? No. Remember, we're talking about absolute values. What we would see on that would be the absolute value of the J1. But you may see reports in the literature where they have a negative J value. You just interpret it the same way you would a positive J value take the absolute value of it and you can draw out the tree diagram the same way.
Is that J2 or J1?
Yeah. J2. Yep. We are going to see this most often in alkenes, where you have two hydrogens attached to the same carbon, as long as they are not equivalent. So if we put a methyl group here, those two hydrogens are now not the same, and they will split each other and show up. And in diastereotopic protons, which we'll get to today or Monday. Diastereotopic protons are actually two hydrogens. They're attached to an sp3 hybridized carbon, but they are not equivalent. So you have an R and an R prime, and this happens when we have stereocenters in the molecule. And those are now not the same, and they'll split each other, and we will see a coupling constant. For the alkenes, they're generally smaller, so we're going to see something like J 0 to 5 hertz, and also for the diastereotopic ones, we're going to see the J2 being around -9 to -15 hertz. Or absolute value being 9 to 15 there. This depends on the angle. When you have a hydrogen that's attached to an sp2 hybridized carbon of an alkene, the angle between the two carbons is going to be 120 degrees, based on the definition of our Vesper models and all of that, back to Jin Kim. So he's got 120 degrees. When you have 120 degrees between these, they don't have as much overlap, and the J coupling tends to be pretty small. So here's our J on the y-axis of this graph, and this is our angle between the two hydrogens of the geminal system, and when it's 120, we're getting near the bottom of this. Now this is not a direct linear, it's not exactly on this line. I would call this more like somewhere in the range around these. That's going to be a little bit broader than just a single line. It's not, if it is 120, it will always be at this point on the line. It's somewhere in that general range, though. When you look at an sp2 or sp3 hybridized carbon, our angle is now 109.5 degrees for a tetrahedral carbon, and we're getting more up in the range between 10 and 20 for your coupling constant. So it does depend on the angle between the two two protons. I just wanted to give you a couple of examples with actual values. So here's a alkene where the two hydrogens are geminal on this one. The J2 or 2 bond HH coupling is going to be 2.0 hertz. So very small, within a range of what our typical geminal alkene proton coupling is going to be. For the other one, we'll look at fructose, which is a chiral molecule, and so the two hydrogens here are going to be diastereotopic. They're both attached to the same carbon, but they are not equivalent. And we will see coupling between the two. In this case, your J1 and HH value is -12 0.1 hertz. So your geminal that are attached to sp3 hybridized tend to be larger, and those sp2 hybridized tend to be smaller.
Then why put a J1 instead of J2?
Sorry, no,
Okay.
supposed to be J2. Two things to be careful of. You're not going to see a J2 coupling if the protons are equivalent swing this over here. So if they're equivalent by either symmetry or rotation, you don't see this coupling. And that's why we haven't seen it very often before. Typically, the two hydrogens that are attached to the same atom don't split each other. But now we're going to start seeing examples where they will, and it's going to make for much more complicated spectra.
On the alkene, the one where it's CH2 on the two,
Right here?
yeah, but like is the substituent?
Oh,
yeah,
right
right
here.
there. Is that one diastereotypic?
No, this one would be, they'd be equivalent because they'd have rotation.
And that one doesn't just because it's a ring.
These two, it's because of these stereo centers actually. These are all stereo centers. Should mention that. And that's going to cause the diastereotypic, which for some reason they put after the explanation in the book, so we'll go over that nomenclature. Here we go through each of the different types. I get it all in the book, I guess. Alright, so J2 coupling, geminal coupling, alkenes or diastereotypic protons. The most common one we're going to talk about, though, is our J3 couplings. These are the ones we've talked about before. They have some additional information, though, that we're going to delve into now. This is your two carbons having two hydrogens that are neighboring. This is going to be referred to as vicinal. So geminal is if the two hydrogens are attached to the same carbon. Vicinal is if the two carbons are attached to neighboring carbons. In the J3 coupling or the 3-bond coupling, we are going to, this is transmitted through transmitted through overlapping adjacent CH bonds. So we're looking at systems where the carbon has a hydrogen attached to it, up here, and the bonds between the carbon and the hydrogen are going to be overlapping and passing that spin information between them. In this case, I have drawn it with the angle between those two being 0 degrees. This is the case where you have two carbons where the two yellow ones are the hydrogens we're looking at. The angle between the two is 0. You get maximum overlap between the orbitals, and you get a pretty good coupling. You can also rotate this the carbon is kind of pointing out in the other direction. So if this was coming out towards you, and this one's still in our plane, this is going to be our alpha equal to 90 degrees. And there is no overlap, or very little overlap, if you have 90 degrees between the two. So now we've rotated these such that they're at 90 degrees. And that's what we're trying to represent on there. So that's a 90-degree angle there. And then if we continue rotating around, the two hydrogens can get to 180 degrees. And 180, it has the two hydrogens on opposite sides. If you remember way back to OChem 1, we talked about the conformations. This is one of the more stable conformations, the two hydrogens being anti and everything not overlapping, this being a less stable interaction. With the 180, we actually still have overlap between the orbitals, though, because you have that little node on the bottom of the orbital that's overlapping with the orbital next to it. So here's the example where we have a 180 interaction. This is actually the maximum, or the best overlap. There are a few factors that influence it. The first one is that dihedral angle, or the angle between them. We have our dihedral angle of alpha, and this is a graph that represents the angle alpha versus the coupling, the three-bond coupling between the two hydrogens. And this is called the Karplus relationship, because Karplus studied all sorts of different compounds and determined that there was a correlation between the angle and the coupling constant between the two hydrogens. At 0 or 180, you have the best overlap between the orbitals and you have the highest coupling constant. So on either end of this relationship, you have larger coupling constants, with the 180 being slightly higher than the 0. 90 has the least overlap and has the smallest coupling constant. So if you had a 90 degree, you're somewhere between 0 and 2 hertz for your coupling constant between the three. And again, we're just talking about the angle between those hydrogens. This will matter a lot more in cyclic structures sometimes, because they get stuck in one conformation rather than being able to freely rotate. There are a few other factors that influence the J3H. One is the carbon-carbon bond length. The substituents. And that can be either electronegative or some type of compression or repulsion. And it can also be influenced by the angle between the carbon-carbon hydrogen angle, if we call that theta. Those angles can also influence it. There's not a direct correlation, or there's not a way to calculate that or use that analogy, but it's something to keep in mind as you're looking at coupling constants. Just because the coupling constant is a little smaller than the Karplus relationship predicts, doesn't mean that it's a different angle. It could be some other factors that are affecting it. And the calculus equation that comes up with this is your J3 for the hydrogen is equal to A, some constant, plus B, another constant, cosine alpha, plus C cosine 2 alpha. And you don't need to be able to calculate this. Generally, or typically, we're going to look at some specific values which actually lead to this graph we have here. So A equal to 7, B equal to -1, and C equal to 5. And that's what gives us this relationship, and that's the one that kind of best fits the relationship that we see. I want to go over a few examples, so I'll just leave it on here and draw them on the board. I'll give you a little bit of extra space to draw them in your slides if you have them. So let's do, cyclohexane. So generally, when we're being lazy, we draw out cyclohexane as a flat structure, but if you remember from OCHEN, it's not a flat structure, it exists as a chair conformation. And it comes back. When you draw it in the chair conformation, remember that we had some hydrogens that are axial, some that are equatorial. So your ones that are pointing straight up and down are axial, and the ones off to the sides are equatorial. This matters for the coupling constant because you have different angles between the hydrogens depending on whether we're looking at an axial-axial interaction, an axial-equatorial interaction, or an equatorial-equatorial interaction. Axial-axial interaction, if you look at the two I'm holding on to, what's their angle? 180. Axial-equatorial, a little closer, maybe it's 60. It's ideally should be right in the middle of the two, and this is, so about 60 degrees if you're looking straight down. And then, let's see, equatorial. It's again close to 60. If you are looking straight down and you draw a Newman projection, all this comes back, doesn't it? We basically divide the circle into 6 equal parts, and so these angles are 60, well, not the way I drew them, but they are 60. Move that out a little. And those are all supposed to be 60, and then your axial-axial interaction is 180. Going back to the Karplus, the 180 has the highest coupling constant. Generally, if you have an axial-axial interaction, this is going to be our largest coupling constant, alpha equal to 180, and our J3HH is going to be somewhere between 8 and 13 hertz, generally for that axial-axial interaction. Our 60 interaction drops off significantly from either than 0 or 180. And actually our 60 is one that we're going to see a lot, because 60 is a pretty common bond difference between two if you have them in a Gauss interaction. And in this structure, your axial equatorial is going to be kind of the medium one. And your coupling there is going to be 2 to 6 hertz. And they call the equatorial the smallest one. It's actually pretty close to the value for the axial equatorial. You don't have to memorize that type of value, but you need to know this relationship and where it comes from. So you need to be able to explain why the axial would be larger than an axial equatorial or equatorial based on the Karplus relationship, and be able to explain why that is a maximal overlap or not.
So if both axial equatorial and equatorial are 60 degrees, why do they have any difference in J value at all?
That's a good question. They're not very different, but they could be slightly different interactions across the ring. But when you look at it directly on, it doesn't look like there should be too much. And it's not a significant effect. We're talking about 1 hertz. I don't know. I can look and see if they have a little bit more of an explanation on it. They're pretty similar. The other example I have is on a alkene, and we'll talk more about alkenes on Monday. But if you have an alkene, it's very common to have either a cis alkene or a trans alkene. No, I totally labeled that wrong. Trans, cis, and the 2 hydrogens are on the same side. In the trans, the overlap is going to be 180. They're on opposite sides of the alkene. So our alpha equals 180. And for our cis, alpha is equal to 0. So this is a case where the 0 comes into play. And as we can see from the Karplus relationship, 0 is going to be smaller than the 180. So these, for the same molecule, your cis is always going to be smaller than your trans, if you're looking at the J3HH coupling. In this instance, there's actually, I don't have a cis or a trans. I'll give you an example that does, though. Typically, our trans is going to be between 14 and 19 hertz, and our cis is going to be between 4 and 12 hertz. The 4's way off, right? Now, that's because it's a relationship. It's not a direct calculation. We can't say for sure there's other factors in there. Let's look at an exact structure. So we're going to look at an alkene that has 3 different hydrogens attached to it. So we'll have HA, HB, and HC. They're all going to have different chemical shifts, and the J3, I'm going to call this the AB. So it's the coupling between proton A and proton B. This has the coupling of 10.3 hertz. Our J3 AC is going to be 17.2 hertz. And since we were just talking about the geminal coupling, our J2 coupling between B and C is going to be 2 hertz. So you can see that the relationship between A and B is cis. It has a slightly smaller coupling constant between, as compared to the A and C, which is trans. And then our geminal is our smallest overall. Now when we look at some alkene systems, this is going to make those alkenes look fairly complicated because they've got 3 different potential, or 2 different in this one, coupling constants I'm showing. There's actually another one, which is on the next set of coupling that we're going to talk about. Any questions on this? Alright. The last one is the allylic, and for our J4 coupling, propargylic, and the W coupling, and then we have J5 coupling, homoallylic and homopropargylic. These are ones that are not very common. For the allylic coupling, we're talking about having a carbon that has a double bond, you have the hydrogen, and then we have a substituent, another carbon, and a hydrogen attached to the CH2 group. So this would be coupling between a proton on a carbon of an alkene to the allylic hydrogen. Propargylic, similar, except in this case we're looking at the hydrogen that's attached to the alkyne, and then the one carbon over on the chain with a hydrogen attached to it. For the allylic coupling, our typical values are going to be, oh, no, we've moved on to 4 now, so it's a J4 coupling, HH, and we're looking at 0 to 3 hertz. And these are, I'll say, sporadic. They do not always occur. They sometimes occur, but they don't always. The propargylic are more common. We'll get to why in a second. And they have a coupling of 2 to 4 hertz on their coupling, and they are typically seen. Again, this has to do with overlap and interaction between. Your book has some nice drawings of this. Here's the overlap. I want to show you with the model. This is my nice alkene pi system above and below the system. And so here's my carbon with the hydrogen attached to it. You can see here in this conformation that this hydrogen is aligned with the alkene system. So you can have overlap between this orbital and the pi system here. And we're looking at this hydrogen over here. But this one has the freedom to rotate, and it often does. And if it rotates to here, now there's not going to be information spread between here and the alkene, and so we will not necessarily see the coupling. So with this substituent, this hydrogen is rotated, so it's not parallel with the alkene, you don't see coupling. And so it's going to just depend on what the most favorable conformation is, depending on what's attached here, and so you may or may not see this coupling. With the alkyne, which I didn't bring mine in, you've got 2 pi systems on either side, right? So you have it going this way and you have it going this way. No matter where this rotates or falls off, it's going to overlap with the pi system. And so you always see, or almost always see that coupling. But again, these are very small couplings, so you have to zoom in close to see them. And you won't see them if you just print out the whole spectrum. Make sure you zoom in on those peaks and make them pretty big so you can see it. So, this allylic one depends on the conformation. And I'll refer you to the book for the very nice drawings. The last one of the J4 coupling is called a W coupling. This is an interesting one that usually only occurs when you have cyclic structures that are very rigid. In a double W coupling, you have 2 hydrogens with the bonds in between them forming what looks like a W. This happens really often when a bicyclic structure like so, where you have a hydrogen going out here and a hydrogen coming out here. And this is the W that we're looking at. So you have a conformation that holds these two hydrogens in a W form, and there's still some speculation as to how this transfers the spin information. Your book gives you two different drawings to look at. But overall, you're going to see a pretty small coupling in this case. Our J is equal to 1 hertz. It was very small, and really only a factor in your rigid structures. Sometimes, if this J4 coupling is less than 0, less than 1, we may not see that high of a resolution on our instrument, so it's just going to lead to broader peaks. So it's going to split it a little bit, but not enough so that it actually goes down in between the peaks, and you see just a slightly broader peak. And sometimes you see that with the J4 couplings. The last two on here are the homoallylic and homopropargylic. So homo means moving one more out. In this case, we're going to look at both sides of the alkene having a carbon with a hydrogen attached to it. And in this case, the two hydrogens are considered homoallylic. Our J5 coupling for that is typically pretty small, somewhere between 0 and 2 hertz. And this again is a sporadic coupling. You may or may not see it depending on what molecule you are looking at. Homopropargylic has two hydrogens on a carbon on either side of the alkyne, and in this case our J5 value is 2 to 3 hertz, and this one is more common than the homoallylic. We have 4 different sets. I just want to leave you with an example that was in the OChem lab. You remember last year, 2 years ago, when you took OChem, you did the Diels-Alder reaction and made this structure. Something like that, I believe. Or maybe this was on the other side. They were taking NMRs of this year, and they're looking at it and saying, it's all singlets. Why is it all singlets? Well, all of these angles in here are probably closer to 90 degrees, and so they weren't seeing coupling that you would expect when you have a neighboring hydrogen. So trying to throw off the OK students this year when we made them take NMRs, apparently. And so just something to think about. Confirmation,